how's that gonna work? I think the next fall, you change that checklist to 9,002. Let's say you finish all my classes that I need to take, and then all I need is just that technical. Right?
Yeah.
So
I mean, that's all you would need.
yeah, because
Yeah, you could finish that up over the summer if you wanted as a framework.
what do we find out?
The end of this semester.
My plan was to take that
Yeah.
and then take that art and then art that other outcomes in the spring with all the regular stuff. And then I'll just need
So could you take those in the spring, or you still have to come back next fall?
if you say, like you said, I'm happy with the tech elective, and I can finish it.
You can finish that up by us in the summer. Yeah.
There's the offer.
Yeah, you know, if that's all you lack and they don't offer it, I'm sure we could find, I would think that we could find some sort of substitute for that as well. They shouldn't make you stay another semester for a single class, in my opinion. So, I say that, I don't have any power about that, but the tech elective I do. But I'm sure we can work something out. I do want to do like an in-class exercise using Code Composer Studio, so I'm going to bring that up. I know it takes a while. It'll be toward the end of the lecture, but
Yeah.
okay. So chapter 8 is on interfacing. And so it's this chapter where we'll learn how to connect the microcontroller to a bunch of different devices. So what there are basically two types of interface. There are serial interfaces where you send one bit at a time, and parallel interfaces where you send multiple bits, typically 8, an entire byte at once. Now you might think that, well, the parallel interface is going to be preferred because it's faster. It's not necessarily true, because with a parallel interface, you can get interference actually between wires that are used in the parallel transmission. So there's a limit to the speed there. A much bigger limitation is if you're transmitting 8 bits at a time, you need at least 8 wires. Okay. That means your wire becomes very expensive, 8 times as costly as a single wire, right? So in addition, the wire becomes bulky, heavy. So almost all modern high-speed serial interfaces, USB, Ethernet, are actually serial in nature. The last common parallel interface was probably printer interface on what was called a parallel port on computers many years ago. That parallel interface on the computer is called the Centronics interface is obsolete. I don't know that you can even find it on a modern computer. The serial interface, the traditional serial interface on the computer is almost obsolete. These computers still have a serial port on them, but most of the smaller computers, most of the laptop computers no longer have the traditional serial interface, or what's called the Rs232 interface. That's primarily been replaced by USB. Our microcontrollers have this virtual serial interface built in that's over the USB cable. But so there are a couple of different considerations that you need to think about when you're thinking about interfacing, and we'll run into these on these chapters. But and then there's more than one serial interface that you'll run into as well. We'll talk about the Rs232 interface today. There's another one called SPI that's also discussed in the book. But some issues are with any interface, just the mechanical interface. So the number of wires that you're going to use, the type of connector that you're going to use. And then there's the electrical specification, which are the allowed voltage, current levels, whether you're going to source or sink current. And then another issue is the data format. You know, when you're sending out data serially, are you going to send the most significant bit first or last? What speed are you going to use? Whether or not there's any sort of error control built in, like parity is a simple form of error control. Do you send a parity bit? Do you use that for error checking? Okay, we're going to focus on, typically you try to use a standard interface, but you need to consider, you know, when you're hooking up a device to your microcontroller, these considerations. In particular, you know, the voltage and current levels are important. You're not going to hook up your microcontroller directly to an industrial sized motor and drive it directly. You're going to have some other source of power to power the motor, and then you can use the microcontroller to actually interface to the motor control and interface to the motor control circuitry. So what you'll find on any sort of interface, wait for this to come up, is specifications on current levels, voltage levels. So this was a table from the book. Certainly making a lot of noise not to be doing anything. The lamp is not on. There we go. Or maybe it's burned out. Well, anyway, there's a table in your book that talks about different current levels for different data families. If you, for example, on our microcontroller, when it's configured for output, it can source or sync 6 milliamps or 20 milliamps, depending on the output drive strength. And that's configurable with we put it in a high output drive, and it'll provide up to 20 milliamps, which is enough usually to directly drive an LED. 6 milliamps may be enough if it's a low current LED. When high or low, so it can either source either 6 or 20 milliamps or sink that much when it's low. And when it's configured as an input, it draws a very small amount of current because it's got a MOSFET transistor input, but it draws only 20 nanoamps. Okay. Well, you have to consider that when you're interfacing to various devices. The other specification is on the voltage thresholds. They're in your textbook as well in a figure. So there's a range of voltages that it will produce on when it's low. I think the output low voltage is specified to be between 0 and 0.6. When it's high, it's specified to be between 2.7 and 3.3 volts. And then on input, any voltage between 0 and 0.825 volts, less than a volt, is considered to be a low input. So when you're reading a voltage on an input pin, anything between 2.475 volts and 3.3 volts on an input is considered to be a high. Now, what we're going to talk about today, the first serial interface, is the Rs232 interface, and then we'll also talk about UART devices. So normally if someone says a serial interface, or especially when talking about computers or microcontrollers, they're talking about the traditional serial interface, again, which is on the back of these computers. It's got a little 9-pin connector on the back of these things. It's called a DB9 connector. And they'll mean this particular, it's called an Rs232 interface. It's the traditional computer serial interface. And a UART is the Universal Asynchronous Receiver Transmitter. It is a circuit that enables serial communication that implements this Rs232. Rs232 is a specification on speeds, voltage levels, currents, and then the UART is a particular circuit. Now the minimal interface uses 3 wires, a DB9 connector was common. So back in the day of mainframe computers, one of you guys want to risk standing up on that table and plugging in that projector? Hunter? Don't fall. Stand up on that table and plug in that projector without falling. I think I can get it with the remote here. So I'm ready to give up. I unplugged that one because the one control would turn them both on. We'll see if this comes on. There's another figure I wanted to show. So typically with the 3 wires, it was just a transmit wire, a receive wire, and then a ground connection. The other thing with serial interfaces is data just going to be sent one way? That's called, or can it be sent both ways? and that's called full duplex versus half duplex. If you're just sending data one way, you typically just need, now, you just need one wire. Not having any luck. Promising. And it's saying nothing's connected. Where that cable comes to. Gonna be one of these. All right. What else I want to say? Let's skip ahead. Okay, modern PCs, which we're using now, a lot of them don't have the serial port built in. You can actually buy a little device that connects to your USB that provides this DB9 connector on it, so it emulates a serial port via what's called a virtual COM port inside the computer. So you can still interface to serial devices. At one time, it used to be common with mainframe computers. You'd have one computer that would actually connect to maybe 40, 50, 100 different terminals. All the terminals connected to the computer via typically a serial cable. And now that this serial interface is almost obsolete, we're using it, virtual serial interface for our microcontroller. You still can actually, hook up a terminal to that serial interface if you're using an operating system that supports it, like Linux. You could actually hook up another terminal to your serial port and get a separate terminal for your computer. So a couple of things though, when you're using especially the Rs232 interface, devices have to agree on what's known as the baud rate. That's the number of bits per second. And the data frame format. So we've seen, and it has to match on both ends. Okay, so there's two pieces of equipment here that you're communicating with this Rs232. It is, our computer and a microcontroller. It might be two microcontrollers that you've connected, or two computers, or a computer and a dumb terminal. The baud rate, we've been using 115,200 bits per second to communicate with the microcontroller. That's fairly common with modern computer systems. On older computer systems, a much slower baud rate of 1,200 or 9,600 baud was common. The other thing is, and this is typical of Rs232, the transmit line is actually high until you want to send a byte of data, okay, to the other device. So it's asynchronous. That's what the A in the UART actually stands for. Another type of communication is synchronous, where you've got a separate clock line, and you would send a bit every clock interval. Here, there's no, the data is clocked, but you can actually start the transmission at any time. And so this would be a start bit to signal that the other computer, other device, that you're ready to send data. And then this is followed by then usually 8 bits of information. Now, it's, I think, shown in your textbook like this, because we don't really know whether this bit is high or low, right? So depending on whether it's a 1 or a 0. So see if I can draw these things. So B1, B2. The other thing too is, do you send the least significant bit first? Time going to the right, do you send B0 first or B7 first? That would be another thing that you would have to consider. B4, B5. Gosh, making these things too big. B6. B7. So this is showing transmitting 8 bits, which is common, transmit a byte at a time. Another common format at one time was actually a 7-bit data word, actually, because the ASCII code is just a 7-bit code for traditional dumb terminals. So you could transmit just 7 bits with the interface to a terminal. And then after that, there would be 1 or more stop bits to indicate that you're done with the transmission. There might also be an additional parity bit, okay, that's transmitted after your 8 bits, okay. There's several common baud rates. 1200, 9600, 115.2 are common. Okay. A frame format of 8N1, meaning 8 data bits, no parity, and 1 stop is standard. Okay. So typically, we'll talk about how to configure the microcontroller. Typically on the PC side, you configure it through a menu in the application that you're using. So there's a terminal, a virtual terminal built into Code Composer Studio. You could also use PuTTY to do the interfacing. Okay. There's some other stuff here I was going to show you on the screen, but maybe if we can all pull it up on our Code Composer Studio together, we'll try and work through it that way. Sorry, I can't show you what's going on the screen. But let's actually create on Code Composer Studio. We're going to write a hello world program that directly communicates with using the UART. Okay. Now we're going to use some of the provided routines. In UART.c, but we may change them a little bit. So create a new project and maybe call it UART hello or something like that. empty project with a main routine. Now, to this project, go ahead and add the uart.c and the uart.h. Now, normally we've linked to them, but this time copying them into the project directory because we're going to modify them. And I want to modify our copies instead of modifying the originals. So, right-click on the project name, and then say add files, and then navigate to your source directory, select the uart.c and the uart.h, open those, and then now in the little pop-up window, select copy files instead of linking to the files. And we'll come back to this, our main program in just a second. But go ahead and open up uart.c. And there's a lot of stuff in here that we don't need to worry about today. But scroll down to, let's look at uart out char first. And let me give you a little, so while you're looking at that, let me give you a little information. The MSP 432 has 4 UARTs. They're UC A0 through UC A3. They're on ports 1, 2, 3, and 9. So, and we've been using some of these ports as general purpose IO ports and selecting them by writing particular bits to the selection registers. Well, now we're, instead of setting them up as general purpose IO, we're going to set them up actually as an alternate function so that they actually operate as UARTs. Now, these particular UARTs, because they're from our microcontroller, actually only provide output levels of 0 and 3.3 volts. So they're not Rs232 compatible. You need an interface chip. So if you're going to use this to actually directly connect to a computer or a terminal, you've got to figure in the textbook of a particular interface chip used to do that. Now, if you're going to have 2 microcontrollers talk directly, then the voltage levels are compatible and you wouldn't need to do that. But the other thing that you need to know is UCA0 is used for the Launchpad USB virtual COM port or virtual serial port. Okay. So this is the one we have to configure when we're talking to the terminal that's in Code Composer Studio. Transmitting a byte is so very much like setting up the GPIO. We have to write to particular control registers or registers in the microcontroller. To transmit, we wait until the transmit interrupt flag. So this is a flag is just a bit. So this is UCTXIFG in the documentation. It's bit 1 in a particular control register. In the interrupt flag register, which is UC, for this one, it's UCA0 interrupt flag, it's IFG, interrupt flag is 1. That means that the transmit buffer is empty, which means that you can write another data byte to the data register, okay, for transmission out the serial port. So we'll see this in the software. Once it becomes 1, we want to reset the flag, set it back to 0, and then write a byte to UCA0, the transmit buffer, TXBUF. So if you look in uart.c and you look down at the out char routine, it looks like it's void uart out char, and then this is just byte char data. And then it's got a while, it's waiting on this flag to be set to 1. So it's that register while UCA0IFG, and what it says bit 1, right? So that would be a mask of 0x2, so bit 0, bit 1. While that's equal to 0, we're going to busy loop. He has just the semicolon there. Okay. I like to put braces to show there's an empty body there for the busy loop. Okay. But this is just going to sit here until this flag is 1. We have to wait until the previous byte, if there is one, was transmitted. When we reset the microcontroller, this flag is set to 1, and we can transmit the first byte immediately. Okay. But once we start the data transmission, we have to make sure that this is 1 before we can write another byte out to the data buffer, the transmit data buffer. And then it just resets this flag, 0 IFG, and it would be and equal not 0x2. We want to reset that back to 0, okay, so that when we, so then it'll be set back to 1 automatically after we transmit the next word. Doing it this way is not going to modify any other bits in that register, right? And then the last thing we need to do is actually just send our data to UCA0 TX buff is equal to R. So this will put our data into that register, and then the hardware takes care of the rest. We'll transmit our 8-bit byte serially out over this transmit line. If you look at the in-char routine, which is right above that, it's very similar. It uses bit 0 because it's ending with a 1 here. Again, waiting for that to become 1. When it becomes 1, that means a complete byte has been read by the UART, and so can now be transferred into your program. And again, we clear the flag, and then now it returns that byte to our calling routine, whatever routine called nchar. So those are the two input and output a character at a time routines. The other thing that we need to do is actually initialize the UART, and that's the first routine at the top. There's a lot of stuff in there, you have to look in the user manual for all of this. There's some information in the textbook, but you can configure the number of the data length, whether it's 8-bit or 7-bit, the number of stop bits, the number of parity bits or no parity. It has a special mode where you can actually do addressed serial, which is a little bit unusual. And then you can also set the baud rate in the UART init routine. Okay. So what we're going to do is actually for our little main program. For our hello world, we've got the watchdog timer here. And then we're going to call our UART init routine. And then in our while loop, we'll need a int I equals 0, I less than string length of str I plus plus, and then uart out char, was that capitalized? Char, and then it would be string I. I probably left out some header files, so we'll come, so enter that, see what we got in our main routine. Okay, I think I've got all that entered. And we will also need, although it may compile without it, I'll need probably the header for string length, although it's just giving me a warning for string length declared implicitly and outchar declared in also implicitly. So we can get rid of the warnings by including the header files that contain the prototypes String length is in string.h. Okay. And it looks like outchar is not spelled the way I spelled it. So how is it actually? Is it not in the header? You may not have the outchar one. It's actually not in uart.h, so it's not actually doing anything for us. We can actually just add the prototype at this point. It doesn't matter. We can go ahead and just flash it to the microcontroller. And now you want to either bring up PuTTY or bring up the terminal that's in Code Composer Studio. And then on the, so for the terminal, there's that little icon where you set the terminal settings. Mine's connected to COM4 at 115.2. Data size of 8, no parity, 1 stop bit, all in the oh, I forgot to call UART init. Did I have it up there? Yeah, but I didn't have it here in my code. So is it working for you guys? It's not working for me because I didn't initialize the UART. Are you seeing anything in the terminal? Seeing hello world. The reason it's coming in at a diagonal is actually, if you look at the other code here, whenever you send a new line, it automatically sends a carriage return. But we don't have, that's not built into the UART outchar. So it's just going down a line. It's not returning to the next line. So if you put a /r here after the /n, which would be a new line, and then a carriage return, it should look a little nicer. Okay. So what you see is, kind of on a diagonal, hello world, hello world, hello world. But if you look actually, so we're directly communicating with the UART here, okay, instead of using printf, for example. So what we've done in the past, and this might be typically how you'd work with the microcontroller. To use printf, that's actually a software configuration thing. We call, output init to configure our library so that printf output goes to the UART. And scanf input comes from the UART. That's what the output init routine that we normally call does. If you call printf right now without calling output init, without redirecting to it actually goes into the debugger. But now we're communicating directly with the UART. Is everyone seeing stuff on the screen, on the terminal? Yes, no, some of you are. Okay. Okay, one other thing that we can do. So let's go into the uart.c and let's look at the init. Now, you have to read through 40 pages of the user's manual to figure out all of this stuff. That's why it's nice to have template code. And it's actually fairly well documented. It says the baud rate here is 3 million divided by the desired baud rate, which is 115.2. Do you see that? Someone have a calculator? Let's change the baud rate to 9600. What is 3 million divided by 9600? I got my phone. $312.5. So it's called 313. So where it says UCA0BRW, which is the baud rate word, change the 26 to 313. And then I'm going to go back into my main program and add the \r. It can actually be before or after the new line. And then recompile. And reflash. Forever. And you guys may be ahead of me, but now my terminal's not showing anything at this. Well, it's showing what was there before. Right? It's because the baud rate doesn't match now. My microcontroller is outputting bits at a baud rate of 9600. My terminal, my virtual terminal here in Code Composer Studio is actually expecting data at 115.2. So close this terminal and then reconnect on the little icon and then change the baud rate now to 9600 from 115.2. Okay. And now at least for me, I'm seeing hello world again. Okay, because the baud rate on my terminal matches the baud rate at which my microcontroller is communicating. Is everyone seeing that? Another thing that's interesting, you'll run into this problem often, so close the terminal again, change the terminal settings instead of 9600, say 4800. On my terminal right now, it looks like it's interpreting the carriage return. I'm just getting garbage. Okay, I'm seeing wrong characters. Let me try different baud rates. At 9600, let me try, see what happens at 14.4, just one above. Now my whole screen is actually just garbage characters, right? Because the baud rate is not correct. So it's misinterpreting the bits that it's seeing. Okay, so actually I remember Andrew had that issue earlier in the semester here when we were trying to use the terminal. And the baud rate on the terminal was not at 115.2 and the microcontroller is set at 115.2. And you just see garbage on the screen here. It's because there's a difference in which the rate at which the terminal is sampling the bits. It's assuming they're transmitted at one rate when they're actually transmitted at a different rate. So, and if we set the baud rate back to 9600, And then you see the output correctly. So any questions about this? There are other things in the uart.c, where we could change the number of stop bits, but again, you'd have to make that same change in the terminal. Okay. Now also remember that we've changed the baud rate in a copy of uart.c, hopefully, and not, it's still 115.2 in our uart.c that we're going to link into our subsequent projects. But make sure your terminal is set up at the 115.2 or whatever speed you're matching to. Any questions? All right, that's it for today. See if we can't get the lamp replaced in this thing or figure out what's going on. It was a brilliant lecture today, so best one all semester. Unfortunately, back to mediocrity from now on. So. The update on residential Nevada stop counting. Oh, so they're not done. They just stopped. They took a break. Biden's ahead there, or still ahead? Was ahead by 0.6%. What I don't understand is, they still have these states showing red for Trump, but the odds now are of Biden winning. The mail-in, yeah, they're expecting those to be heavily Democratic, but say that again. 80% of the undocumented counted. Okay, and they still have a lot to go. Okay. So they're expecting Pennsylvania to go 1.5 million left to go.
Oh, even without Pennsylvania, they still might win Biden. Because Nevada, Wisconsin, and
right, which I know they're close to.
Okay. But
that'd be right. That'd be exactly 270.
Yeah, the Trump campaign just issued a revote for Wisconsin.
Okay.
So
it's gonna be a while.
Yep. Yeah, it is very. There's one vote again because they're counting more.
So what? It depends on your computer. You can go into the device manager and look. It'll tell you which COM port it's using. But I think on yours it was COM3. It could be a COM 100. The example in the book, it's like a 153. I mean, it could be anything depending on the number of devices you've hooked up before that have used virtual COM ports. It just assigns the next available virtual COM port. COM 1 and COM 2 were reserved for the actual hardware serial ports that were on the computer. So usually it won't be COM 1 or COM 2.